Did it beep? Oh, okay. I sometimes feel like my hearing is like just not present like 5% of the time, because in a given like 10 people pushing the button, there'd be like about 1 out of 10 times I just don't hear it. It weirds me out. And then like 1 out of 1,000 times they actually haven't pressed it, and those are the times that I really regret it. Anyway, I will begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for the students. Just pray that you'd help us to use this time wisely, Lord, just to glorify you, what we do here. In your prayer, Lord Jesus. Amen. I think I promised you guys a proof of something. Let me get that out of my system here. So one of the theorems I stated for you guys was that if we had a linear transformation T from V to W, right? In other words, T is linear transformation from V to W, and, you know, V and W vector spaces over a field F, all right? And number one, if V1 is a subspace of V, then T of V1 is a subspace of W, right? And number two, if W1 is a subspace of W, then the inverse image of W1 is a subspace of V. Again, I should emphasize, point number two, I'm not saying that T is invertible, all right? That's the inverse image in terms of set theory, which I'll remind you today how that works. All right, so the proof of both of these is a subspace. It's just subspace test and definitions. These are like very, very fair test question proofs. I've often asked these in some sense or another. So let's start with one. We should do what? We assume that T is a linear transformation from V to W, obviously, right? And let's suppose that V1 is a subspace of V, all right, over F. Now, I want to prove that T of V1 is a subspace of W. So first, I'll for the sake of you guys, let's recall that T of V1. What's that look like? What's T of V1? It's equal to T of X, right? Such that what? Where does X have to come from? The what? V1, yeah. It has to come from V1. So let's let, W1 and W2 be elements of T of V1, right? And let's let C be a scalar in our field, right? Consider T, oh, I'm sorry, we should consider what? We should consider C W1, right, plus W2. We'd like to show what? We'd like to show that's in the alleged subspace, right, this T of V1. We'd like to show that that's again in the image under T of V1. So what do I do here? I guess I'm going to add some, right after that, consider, I'm going to say something else, Consider there exists what? X1 and X2 where? In V1 such that what? W1 is what? T of X1, right? And W2 is what? T of X2. Sorry, poor planning on my part. I could have put that as like a parenthetical comment after the calculation I'm just about to write down. I mean, so it's not absolutely an error if I haven't written it at this point. It's just to me, it's more natural if I write it right there and then use it in the next line. So there's this X1 and X2 in V1 whose images yield W1 and W2. All right. That's by the assumption that W1 and W2 are in the image under V1. But then this is what? This is C, T of x1, right? Plus T of x2, right? Which is equal to what? By linearity of T, right? But V1 V1 is a subspace of V, hence, x1, x2, and V1, right, implies what? Implies that Cx1 plus x2 is where? It's also in V1, right, because it's closed under scalar multiplication and addition. It's a subspace. And what does that tell me? If Cx1 plus x2 is in V1, what does that say about the line right above? Focus your attention. We got this is equal to that, right? Call that thing star, right? So star reveals what? That C1W1 plus C1W1 plus W2 is an element of what? C1W1 plus W2 is equal to T of C1X1 plus X2. In other words, it's T of this is something in where? In V1, right? So this line right here proves that C1W1 plus W2 is actually an element of T of V1. See, there's really not much calculational difficulty in this proof. It's mostly what? You're really struggling with the definition of what the image of a set is, right? I don't think you guys are struggling so much with subspace test anymore, right? You kind of know what that is. The question is how to actually implement it, right? So there's part of it. This then, so we have what? Thus, W1, W2 in T of V1 implies that CW1 and W1 plus W2 are in T of V1. Also, I usually try to do this at the start of the subspace when I'm doing a subspace test theorem proof, right? But what did I forget? I need to show that T of V1 is what? Non-empty, right? So how would you, what's the simple thing that's got to be in T of V1? In fact, it's the only thing I know for sure is in there, because we could have the situation we looked at the other class where we have the zero transformation, right? It could be 0 is the only thing in the image. If we have the zero map, for example, that's really the only reliable candidate here. If you look at 0 is an element of V1, right? Thus, T of 0 equal to 0 shows 0 is an element of T of V1, right, which is non-empty. Consequently, by subspace test, we have proved what? We've proved that T of V1 is a subspace of W. Oh, what did I neglect to even say? There's one other thing we're supposed to check for the subspace test, to be really careful. I warned you guys I would forget to say this sometimes. Notice T of V1 subset of W is given implicitly by writing that T is a mapping from V to W, right? W is the codomain, So if you take some subset of the domain and you look at its images, you can't fall outside the codomain, right? The codomain is the universe of possible places for the range to go. You can't go outside that by construction of function. So, any questions about this? So our typical application was what? What's the usual application of this part of it, part 1? If we set v1 equal to v, then what's t of v? I'm going to bring some duct tape in here one day. I'm just going to lay down put duct tape over this so that, because at some point I'm going to fall. But the students will like it, so I'm conflicted. I don't know. So that's the range. That's the range of t, right? Or you could say the image of t. All right, let's look at the proof of 2, and then I'll try to spend the rest of the time on your questions. Number 2, and actually maybe I should, I'll start 2 over here. Make sure I have enough room for it. So 2, we want to, in other words, prove, what's our goal? Prove that T inverse of W1 is a subspace of V, right? So what do we assume? Again, we assume that T going from V to W is linear over the field F. And we want to have W1 as a subspace of what? W, right? Now, I will remind you guys, because I know that you're rusty, recall that the inverse image of W1, what is that? What's the inverse image of W1? This should be, it's a subset of the domain, right? So basically we take x from V such that T of x is where? Right. So it's the set of things in the domain which map to W1. That's the inverse image. Notice that it doesn't require T inverse to actually be defined as a function, right? Okay. Our goal is to prove that's a subspace, right? So let's see here. Notice that 0 is an element of V, right? Such that T of 0 is equal to 0 in W1, which is, by the way, a subspace of W, right? So therefore, 0 is an element of the inverse image of W1, which is, okay, so we've shown it's not empty, right? Also, to get this out of my system, it's clear that the inverse image of W1 is a subset, right? Again, look at the definition of inverse image. We're taking things from V. Is this a subset of V? Yes. So essentially by construction of inverse image, it's a subset of V. Then what? Next up, we let what? Let's let x1 and x2 be elements of the inverse image. And let's pick a scalar c, right? And c be in the field. So what does that mean? Hence what? Hence T of x1 and T of x2 are where? What's that? I just didn't hear. W1. Yes. All right. Our goal is to show what? Let me write our goal. No, this is not part of the proof, but let me write it off here. We're trying to show that Cx1 plus x2 is an element of T inverse, right, of W1. What does that mean? That means that T, this being in that, means that C Tx1 plus x2 is an element of what? Right, so this is, I need this, right? So what I should do then is I should look at that. What is T? What is T of C1? Consider T of Cx1 plus x2 is what? By linearity of T, that's Ct of x1, right? Plus T of x2. And let me just, sometimes I'll invent other letters, but I'm just going to use a label here, which is an element of W1, which is a subspace of W by star. Right? Because the images of x1 and x2 are in W1. So a linear combination of those is again in W1 because it's a subspace of W. Is that clear? So what does that show us? Thus, Cx1 plus x2 is an element of T inverse of W1. Therefore, Cx1 and x1 plus x2 are elements of the inverse image of W1. And we conclude, which I'm going to write find because it's less to write, we find T inverse of W1 is indeed a subspace of V by the subspace test, right? It's not hard if you keep your eye on the prize, but there are some sort of non-intuitive steps in here, right? When I was in your place, I found this proof challenging because I didn't really fully understand inverse image. Right? And that's okay, but that's one of the things you're trying to learn in here. So if you're like, you think I know this from Math 200, but I don't know this from Math 200 or Math 250, well, I know that you don't know it. And that's why we're going over it again. Yeah. Okay, so fine, great. What's the principal application of 2? We all like apps for things, right? Not really. T inverse of 0, right? That's the kernel of T. That's a subspace of V. Kernel of T is a subspace of V. Because 0 is a subspace of W. And the inverse image of the 0 subspace is called the kernel. And we've learned the kernel is very important, right? If the kernel is 0, that means that the linear map is injective. It's 1-to-1. Yeah. What would it take for the map to be surjective? What condition would we need for surjective? If the kernel has to do with 1-to-1, the range has to do with onto, right? So to say that the mapping is onto is just to say that the range of T is equal to W, right? This would give you surjective. In other words, it's onto, yeah. All right, well, that's what I wanted to prove carefully for you today. So now that I got that out of my system, whatever you guys want to talk about, it's all good. I mean math. My community college professor would tell us, he's like, you come to my office, talk to me about anything. Physics or electrical, engineering, not electrical engineering, but electronics related. Like, I don't want to talk to you about your personal life. It's like, go to a counselor for that. Which is kind of funny because he would talk to students about their personal life. I mean, he was like that, but. Anyway.
Can you explain the inverse image?
Oh, sure. mean, I can try. I think it might be helpful to look at the inverse image of some things that are not linear, just to get a better sense of what it is, you know. Here's one. We could look at something like f of x comma y equal to x. I like this example, x squared plus y squared. So here I'm looking at a function which the domain is R2, right? And the range is R. Okay? And then you can ask the question, what's the inverse image of points in, oh, not the range, the codomain is R. Okay? The range is smaller. What would the range be here? What can you say about the sum of the squares of two real numbers? It's positive. I take you're positive and raise you a non-negative. Positive is a little bit too strong. 0 could be in there, right? So if we look at, okay, so like, what's the inverse image of, say, minus 5? By definition, that is x comma y such that what? X squared plus y squared equals to minus 5. What's the solution set then? What x and y solve that equation? Yeah, nothing, right? So the inverse image of minus 5 here is just the empty set. In fact, if you take any negative real number, right, is the empty set for c less than 0. How about what's the inverse image of 0? What's the solution of x squared plus y squared equals to 0? Right? So it's just this guy, right? It's the 0 in the domain. And then, how about this? What's the inverse of c, given that c is positive, right? What's that inverse image? We're looking for the solution set of x squared plus y squared equals to c. Geometrically, you can tell me what that is. What is it? Well, c is positive, right? I could just as well set c equals to r squared. Maybe then you could tell me what it is. Someone here knows what this is? No, not triangle. Oh, but we could see a triangle in it. That's true. Fair enough. Here, I'll get you guys started. If we draw this circle, if we pick a point, x, y, on that circle, you're right, there's a triangle. I see why you're saying that. You're thinking about this triangle, which is inside this circle, right, with radius r. I mean, that solution set is a circle centered at the origin of radius r. So, inverse images of singletons, the inverse image of a singleton, f inverse of a point, is called the fiber over P. Usually I think about non-empty fibers. In fact, some people might force that into the definition of fiber. I'm not enough books right in front of me, but basically what I'm showing you here is that we can look at this, right? And we've got the center point, right? And then we've got these concentric circles around the origin. These are the fibers of this map, right? like that. And if you want to picture it, F is this map, right? And what does it do? It maps the origin, right? It maps this to the origin over here, right? And then if the circle has, say, radius, and then it's mapping the rest of them up to this part, 0 to infinity. So the inverse image here, the fibers of this map, they're either just the origin, right? Or they're a whole circle. So is this map 1 to 1? What does it take for a map to be 1 to 1? What do we have to be able to say about the fibers? The fibers have to themselves be singletons. Every fiber has to be a singleton is what it means for it to be 1 to 1. So F 1 to 1 means each fiber is either a singleton or what? A singleton is a set containing one element. One of these fibers is not a singleton. Actually, so, excuse me. The one I'm thinking of is, of course, the empty set, right? I mean, we got 1 to 1 doesn't care about whether or not there's, a fiber being, what does it say if a fiber is the empty set? That says that there's something in the codomain which is not reached by an image, right? So if there's a fiber that's the empty set, that means that the mapping's not a surjection as stated. So some of you guys are math majors. It's time to have a talk. Something a math major should think about as they go on at some point or another is, how to take a given function and convert it into a bijection. Can you do it, right? How would you take this function and change it into how would you find a natural bijection which was related to this function? I'll get you started. Let's say G is mapping from something, right? I don't know what that something is yet, but surely we should just do 0 to infinity, right? So we want to keep kind of the same formula. We just throw at just chop the codomain down to the range, right? Then you can make any function into a surjection by just taking the codomain and making it small enough to just be the range, right? That's easy. But how do we make this function, how do we trade this function for something related that's 1 to 1? How do you do that? 1 to 1 means each fiber is either a singleton or the empty set, right? So we got rid of the empty set by putting the range being 0 to infinity, the codomain being 0 to infinity. Any ideas? We need to make the domain smaller as well. How should we make it smaller? You guys look tired. I'll help you. So just pick any ray from the origin. Whatever, like this, and just say, if you look at that, right? If you look at any ray from the origin, if you use that as your domain, right? Then if you look at each fiber, it only hits each fiber once, right? This green thing is called a cross-section. Cross-section of the domain. It just cuts through each fiber just once. And so we'll give it a name. I'll call it U. So if we do G goes from U with just any ray, pick any ray you like, then that will define, where G of xy is what? X squared plus y squared, same formula. I'm just playing games with the domain and the codomain to convert it into a bijection. So here's some more Math 200 kind of stuff for you. The set of fibers, the set of non-empty fibers, all right? Set of non-empty fibers on the domain, it actually partitions the domain. If you pick any point in the domain, it has to be in a single fiber. That follows by the single valuedness of the function, right? So you can argue that the fibers partition the domain, and what does it mean if the fibers partition the domain? What is that? Partitions are non-empty partitions are in one-to-one correspondence with what on a set? Equivalence relations, right? So fiber equivalence is actually an equivalence relation. You can say that x and y, x is equivalent to y in the domain, right? In the domain of a function, if and only if f of x is equal to f of y. F of x equal to f of y means that x and y are in the same fiber. So this is a so-called fiber equivalence that will partition the domain into non-empty fibers. And so to find a cross-section is just to pick one thing in each one of those equivalence classes. In the example that I've just pictured, you can actually see how to make the cross-section, and you can see why we would call it a cross-section. It's really kind of like just slicing, so you get one thing in each. I'm not sure that was the answer you were looking for, but these things I discussed in chapter 1, but somewhat briefly. Yeah. Yep.
In the last example, then, what is the inverse image of like the F inverse of C?
This one?
Yeah. Like, do we have an answer?
For a given C, it's just a circle. So if I, for example, if I put 1 here, right? Then that would maybe be the unit circle. I mean, you could use the cross section. You could just use like this. One choice would just be 0, infinity. Cartesian product with just the 0. That cross section would just be geometrically be this guy. Yeah. There's lots of different choices. The choice of the cross section is by no means unique. There's infinitely many different ways you could chop the domain down to a smaller thing that made the function into a one-to-one map. But we can always play this game. We can take a function, make its domain smaller such that it becomes injective, and make its codomain smaller such that it becomes surjective. So you can take any function and through these two things elevate it to a bijection if you want. This is the set theory, in fact, which is behind the theorems which tend to confuse you guys more in these courses. For example, the fundamental theorem of, well, not the fundamental theorem, the first isomorphism theorem is basically linear algebra added to this thought process. But linear algebra makes it easier, right? What's the inverse image? If we're talking about a mapping from, suppose we're talking about a mapping from Rn to Rm. You guys tell me. What's T inverse of a subspace? What's this? If W is a subspace of Rm. Can you describe to me what is the inverse? What are the possible? What does the inverse image look like? I mean, it's. Well, this is not what I'm trying to say. What's the inverse image of a singleton under a linear map? I mean, what's the difference between this is not very much a nonlinear map, right? What's the inverse image of a singleton under a linear map look like? Anyway, you guys had a question about the homework. I could go on about this, but it won't be helpful if I keep going on. I have a suspicion. I mean, we could try. Fine, I stated a question. Let's at least look at it for a second. What's the inverse image under a linear map of a singleton? How's that look? Suppose we have T from V to W, right? And we're suppose that, W naught is an element of W. And we look at T inverse of the set containing W naught. What's that look like? By definition, that's what? That's X and V, such that what? Mm-hmm. T of x is in the set containing W, right? T of x is in the singleton. So, what was that actually? I mean, okay, there's the, right. You said T of x is an element of W naught. Of course, I mean, this we can restate in terms of equality, right? And that's probably what you just told me, and I just ignored you. You said T of x equals to W naught? I mean, that's equivalent, right? So what is that? How about this? If y was in the kernel of t, and x was in t inverse of W naught, right? Consider that t of x plus y equals to what? Right, because t of y is 0 by construction of the kernel, right? Which is what? Right. That's W naught by construction, yeah. So apparently this inverse image, we can add anything. We can add anything in the kernel, and it's still in the inverse image. So what this shows at the moment is that, let's see here, x, I should probably call this x naught. Let me call this x here x sub naught, okay? The x naught after the x naught. I mean, why not? No, there's no y naughts. There's only x naught. So x naught, I'm sorry, I'm an idiot. But you knew that already. X naught plus the kernel. So what should x naught plus the kernel of t mean? This is a new note. I have not, this is, for you guys, forbidden notation, unless you were to define it for me. So this is your chance to find this notation for me. What should this mean? What should a point plus a set mean? How about this? X naught plus y such that y is in kernel t. So it's just the set of, you just add x naught point y's to the set you're adding to, like that. So my point is the calculation above shows that x naught plus the kernel t is a subset of what? It's a subset of the inverse image of W naught. Claim they're equal. So to show that they're equal, what would we have to prove? Ah, right. So we've already got the one containment. So we need what's missing. You said the inverse image of W naught is a subset of this set, right? So how should we show that? How do we show that how do we prove this bit right here? So let's pick Z, for lack of imagination. Well, actually, I've used my other letters up. Z in the inverse image of W naught, right? Then what? So T of Z equals to what? W naught, right? which, by the way, is equal to what? 0. Oh, excuse me, how about this? Words. Which is equal to, my brain is freezing. Help me out. We know that W naught is equal to, by construction, T of X naught, right? What is it? So we have that T of Z is equal to T of X naught. What's that tell us? That tells us that T of Z minus X naught is where? That's equal to 0, right? And what's that say? Remember that proof we did recently about 1-to-1 and the kernel being 0? This is kind of that calculation again. So we've got Z minus X naught is where? In the kernel, which is to say that Z minus X naught is equal to K for some K in the kernel, which then tells me what? Z is equal to what? X naught plus K, which is exactly something, it's X naught plus something in the kernel, which is to say that Z is where we want it to be. It's in X naught plus kernel T. This is currently missing from my notes, but it probably should be in there now that you guys have driven me to this discussion. So thank you for your question, Emily. I don't think this was your desired outcome, but it's actually a good one. Adding a section in my notes which actually went through this discussion would be a useful addition. So let's summarize the discussion. What does this say about the inverse image of a linear map? How big is it? Here's one. T of X, Y, Z equal to X comma Y. It's what? What did you say, Bethany? It's just one? No. What's the kernel of this map? Is this linear? It is. Here's the standard matrix. I know you guys haven't watched the video yet, so sorry about that. The standard matrix for this one would be, we're going from R3 to R2. So we're looking for a 2 by 3 matrix that when we multiply x, y, z, we get our output, which is my x, y, right? So like, what's the matrix that goes here? One, 0, 0, 0, 1, 0, like that. So this, by the way, guys, is the so-called standard matrix of T. Okay. But anyway, my point here was, what's the kernel of T? I mean, we can just calculate it directly. We're looking for what? X, Y, Z? Such that T of X, Y, Z, which is, by the way, X, Y, is equal to 0, 0. So what is the kernel of T in this case? Yeah, apparently X is 0 and Y is 0, but what about Z? Z is free. I'm assuming we're working on from R3 to R2. I'm sorry, I never wrote that here, but So that's the kernel. It's one-dimensional, right? Let's see here. So if I was so foolish as to hazard a picture of this, here's the, I have not my best choice of examples because it makes graphically my life hard. But here's your y, here's your z. The kernel itself is just the z-axis. That maps over here to the origin, right? This is what T does. It maps the whole kernel to the 0 in the codomain. But if I pick another point, right? Say this one. What would that be? Something like 1, I don't know, 4. What's the inverse image of 1, 4 under T? Well, if you believe the general calculation we just did, it should be 1, 4 plus the kernel of T, right? Excuse me, it should be the inverse image of the set containing 1, 4, right? Still, I'm an idiot. What is one point which maps to 1, 4? T of blah equals to 1, 4. Can you give me my quote-unquote x naught? In our previous discussion, what is the x naught? Okay, you guys do not follow me yet. Oh well. 1, 4, 0. That maps to 1, 4, right? So in particular, 1, 4, 0 is in the inverse image of 1, 4. So my claim is that we can look at the point 1, 4, 0 plus the kernel of T, and that is the inverse image of the point 1, 4. Graphically, I can even hazard a picture. So it's this vertical line, basically. So the fibers of this map, they're vertical lines. If you wanted to take a cross section, just look at the xy plane, right? If you just look at the xy plane, then we could, basically this map just becomes the identity. If you just replace, you look at T as being a map from, let's say, R2 cross 0 to R2. That cross section, in other words, that's just the xy plane in R3. The xy plane embedded in R3. So if I limit it to that, then the fiber just hits. If you look at this set here is really just, right, so it's just hitting that there and there. It goes on and on, of course, but I'm going to try to put it in words again. The inverse image of a singleton with a linear map, what it's going to look like is a point plus the kernel. What is a point plus the kernel? They're not always subspaces, right? Is this a subspace? Well, no, it's a line not through the origin. It doesn't have 0 in it, right? It's not a subspace with respect to the standard vector space structure of R3. But it's awful lot like a subspace, right? It's just a shift of a subspace. These are sometimes called linear manifolds or affine subspaces or something. But anyway, the point is it's just it's a parallel translate, if you will, of a subspace. And that's what the inverse image under a linear map looks like of a singleton. It's always a parallel, just a translation of the kernel. The inverse image for a linear map is as big as the kernel is. When the kernel is 0, this just collapses to a point, and the inverse image is just a point, which means that the function's 1 to 1. But if the kernel is bigger, then the inverse image is not just a point. It's big. It's as big as the kernel. But it's also boring. It's always just like a parallel translate of a subspace. It can't be circles.
In the example before right there, does it matter that Z is 0 or it could have been anything?
Does it matter that Z is 0? Oh, for the x naught?
Yeah.
No, it does not matter. We could have made this pi. And it wouldn't have made a difference. Right, then I would be basing it off this point, right? So you just jumped ahead a bit. This is, by the way, this theorem that we will prove in a few days is that if we have x plus w equal to y plus w, that's true if and only if y minus x is an element of w. So these are called W cosets. W cosets. So x is the representative, y is another representative. The representative is not unique. You can always like shift where you're representing the coset. The label is by no means unique, which corresponds to the fact that we can always take x naught and shift it by anything in the kernel. It still works as a quote-unquote x naught, because it still will map to the same, in this case, 1,4. This is not where we're supposed to be today. Let me get back to standard matrices and things that are in your, this is not in your homework, right? I mean, this is going to, this conversation will benefit you long-term in this class, but short-term, maybe not so much. Yeah? You're like, you can blame Emily, but you started it. Fair enough. So let's redeem the day. We have 15 minutes, right? So example. If we have t of x, y equal to 3x minus y, 4y, find standard matrix. Of t, which is a mapping, let's say, from R2 to R2, to be clear. Okay, so in the videos you guys have not watched yet, my apologies. I was trying to get those done earlier yesterday, so you'd have a chance, but then, well, anyway, things happened. So, I'm not sick yet. I mean, I went home Monday to a vomiting child. This usually doesn't turn out well. I'm kind of half expecting to miss Friday when it hits me or something, because I've believed in, like, I start to believe in the permanence of stomach bugs, like in a house. Like, I think that they will transfer. Like, transference is non-negotiable. Like, it is going to happen. I bought a can of spray Lysol. I've gone nuts with it, but I don't know. I just have this feeling like something's going to happen. It can't just be one kid, right? It's got to be more. Anyway, so standard matrix, sorry. And again, so I defined basically T is the standard matrix, and you can calculate it. It's T of E1, T of E2. I mean, this is effectively a definition for the standard matrix. So from this perspective, it is T of 1, 0, T of 0, 1, which you can easily calculate as what? 1, 0 gives me 3, 3, 0, right? And 0, 1 gives me minus 1, 4 when I plug it in. So in our usual notation, that's 3, 0, minus 1, 4. Of course, the other way, that's the one way you could do it. The way I usually do it is this, guys, though. The matrix I'm looking for, x, y, equal to what the output is. So this is what I usually do, guys, is I write that down, or I think about it in my mind, and then I just fill in the box with what has to be there to accomplish the multiplication, right? So if you look at it, to get, to get 3x minus y up top, that means I've got to put a 3 here and a minus 1 there, right, to get that. And to get 4y from multiplying a row times xy, I've got to put 0, 4. Of course, this is not at odds with the other way of doing it, right? Now, in the video you have yet to watch, I prove, among other things, that if we calculate the standard matrix of a composite of two linear maps, it's actually the product of the matrices composed. So this is kind of neat. In particular, a nice application of this would be like t squared. What's t squared? T squared, by definition, is the composite of t with itself, which would make sense provided that t is the mapping from like Rn to Rn, where n is whatever. I mean, it's a mapping from the same dimension to the same dimension. So that would be, by the thing I proved, tt, right? Which, by the way, is t squared. So that's kind of neat. The standard matrix of the square of a map is the square of the standard matrix of that map. How would you calculate t squared directly here? What's t squared of xy? This is t of xy, right? So let me just sort through it in terms of map theory, map theoretic arguments. So that's t of 3x minus y, comma 4y, right? Which would be what? So I take 3, and I put whatever's x, in this case 3x minus y, and then I subtract the y, which in this case is 4y. Then I'm supposed to do 4 times the y, which in that case is 4y. So if you look at it, direct calculation of the square map looks to me like 9x minus 7y, right, and 16y. So you can see from that that the matrix of the square map is what? We've got a 9, a minus 7, a 0, and a 16, right? But the other way you could calculate the action of the square, or the map composed with itself, would just be to, well, square the standard matrix. So here the standard matrix was 3, minus 1, 0, 4, right? So multiply that by itself. You guys can multiply matrices. What do we get? We get minus, 9. Looks like a 9 there. 0. Minus 3, let's see here, minus 3, minus 4, minus 7. And 16, so. There you go. There's an example of this thing I wrote in the abstract in green up there in practice. So that's the standard matrix of a linear transformation. Now, when we have the full class together, we'll talk more about how do you detect whether the transformation's a surjection or an injection in terms of the standard matrix, all right? It's, well, if I say anything, I'll say the whole story, so let me stop. But I have not yet addressed that. I think you have some homework questions about that. The theorem is pretty simple, though. I mean, like, okay, so there's that. Any questions about? Yep.
Well, not about that, but like, I have a problem that's like that.
Oh, okay.
I understand doing like multiplying the S's.
Which one is it? I have it here somewhere. 79?
Just the X, Y, U, V, and W are specific. What are we supposed to do with those?
79? Well, let's see here. So suppose we had S of UVW equals to 2U plus W comma 3V minus W, right? Then this would be something like from R3 to R2. And so the same song and dance. This is, some matrix 2 by 3 times UVW. And so what do I have to put there? Well, I got to put a 2, a 0, a 1, a 0, a 3, a minus 1. And so there you go. That's the standard matrix of S. If I was to try to compose that S with my T, could I do it?